Welcome to the O-Level Chemistry Lecture Series. Today's topic is on organic chemistry. This is quite a big topic, so the video will be split into a few parts, which you will see later. Probably alkenes, carboxylic acids to esters, and then macromolecules. So let's begin with organic chemistry. The first thing you need to know is the term hydrocarbons. You will hear this term mentioned quite a bit of times during the slides. So what are hydrocarbons? They are basically compounds which are made up of only carbon and hydrogen. So for example, this is the formula for methane. So methane, CH4, comprises of only carbon and hydrogen. 4 hydrogens in fact. So this is a hydrocarbon. Ethanol, C2H5OH. You will see more of this molecule later on, this ethanol. Ethanol has an oxygen here, so this is not a hydrocarbon. So only compounds with carbon and hydrogen and nothing else are called hydrocarbons. So why are organic compounds so useful? Simple reaction here exemplifies it. Basically, you can burn them, and when you burn them, you get heat. You get heat, and the heat can be used to drive many other chemical reactions. So, for example, you burn your petrol in your cars. The heat is used to make air expand to push the pistons in the car engine, and your car moves forward. So, the effective use of organic compounds, such as hydrocarbons, such as methane, is basically to generate heat. They produce energy during this chemical reaction. So you would have come across these two reactions before, complete and incomplete combustion. I won't dwell on it too much. Basically, during complete combustion, you will get carbon dioxide and water. Incomplete, you would sometimes get carbon monoxide, sometimes you will get carbon here, or we sometimes call this soot. Okay, so here are some of the fractions from petroleum after refining. The refining process is basically a huge fractional distillation process. This is a fractional distillation column on a massive scale, and it works based on the different boiling points of the different fractions. So this tells us that crude oil is actually a mixture, and when you warm it up to different temperatures, the different fractions will evaporate off. So here we have some fractions here: petrol used in cars, kerosene as jet fuel, diesel oils in buses, in trucks and stuff like that. And we will cover a little bit more on this later on, that the properties of the fractions, they actually vary with the change in the number of carbon atoms. Later on you will see more about this one on the various subsets of alkanes, alkenes, carboxylic acids and so on and so forth. Alright, so let's move on to the lesson proper. There are 4 classes of organic compounds which you will need to know, and they are all arranged in a homologous series. What are homologous series? So before we go into the actual classes of compounds here, let's explain what is the term homologous series. So basically, the homologous series is a trend. It tells us this trend, the same general formula, same chemical similar chemical properties, and gradual change in physical properties. Sounds very weird, right? But don't worry too much. Later on, you can see. So basically, it means that if I have one original starting compound, I can predict what is the next compound. I can predict what is the next compound. So this 3 together is what I call the homologous series. So this is a human, this is also a human, this is also a human, this is a bit bigger, it is a little bit bigger than the previous one. Later on you will take a look. For organic chemistry, the homologous series is defined by 4 different strands. So first one, it differs from the next member by CH2. So basically, if the first one is CH4, the next one will be C2H6. So the difference is CH2. Next one will be C3H8. They are very similar chemical properties. So if I burn methane, I will have carbon dioxide and water. If I burn this 2-carbon hydrocarbon, later on you will know that this is called ethane, I will also get carbon dioxide and water. There are physical properties which show a gradual change. So Earlier in the previous slide, we mentioned that as the number of carbon atom increases, the physical property changes slightly. So if you recall your chemical bonding topic, CH4, the predominant intermolecular force is van der Waals forces. So the strength of the van der Waals forces, it depends on the MR of the molecule. So as my MR increases, as I add one carbon, and it comes together with a H2. So as I add one CH2, the MR increases, and as a result, the strength of the van der Waals forces between the methane molecules increases. So this is the van der Waals force between methane, and this is the van der Waals force between ethane. So the strength of this van der Waals force increases. So as a result, I need more energy to overcome these forces, which means that the melting and boiling point will increase as well. The last one is that it can be made by similar methods. So later on we will see more about this one when we break into the respective subsets for the organic compounds. So here we have it, the four which we will be doing: alkanes, alkenes, alcohols, and carboxylic acids. So alkanes, simpler structure, that's why we are doing it first. This C single bond C, this line here represents a single bond. So this line here represents a double bond. This line here represents a single bond, single covalent bond. All these are covalently bonded. Right, so we touch on the alkanes first. Very simple class of compounds, very simple reactions. So they form a homologous series consisting of saturated hydrocarbons with the general formula CnH2n plus 2. Saturated hydrocarbons basically means all single bonds. There are no double bonds at all. Okay, so every single bond in the molecule is a single bond. And they are in a homologous series. Why? Because each one varies by only a CH2. So the first one CH4, second one C2H6, and so on and so forth. Notice they just keep adding one single CH2 from the previous member in the homologous series. And they are all single bonds, so this is a saturated hydrocarbon. And the general formula here is CnH2n plus 2. How is this derived? So for the first compound, it's C1H4. The next one, you add one CH2. Next one, add one more CH2. So CnH2n plus 2, this general formula allows me to predict what is the next member in the series. So if I were to say, what is the molecular formula of an alkane with 3 carbons? So if you sub this into the formula, C3H, 2 times 3 plus 2 is C3H8, propane. So what is the molecular formula of the fifth member of the alkanes homologous series? It will be C5H12, 2n plus 2. Right? Simple. Okay, so let's quickly do checkpoint 1. We can pause the video now. Continue when you are done. So ethane is an alkane with 2 carbon atoms. Draw the structural formula of ethane. So let's recall, what is the general formula for ethane? So ethane, by the name, implies that this is an alkane. Alkane's general formula would be CnH2n plus 2. So if there are 2 carbon atoms, it means that the general formula, the molecular formula of ethane would be C2H6. So to draw the structural formula of ethane, it is simply 2 carbons. The carbon backbone always joins together, and each carbon, if you recall, has 4 valence electrons, which means that after one carbon, 1 electron is used to form a bond. There are 3 more left. Every single electron must be bonded to something. So it is bonded to hydrogen. 1, 2, 3. 1, 2, 3. So this is the structural formula of ethane. 2 carbons, 6 hydrogens. Count to make sure that each carbon has 4 bonds. Very important. And to draw the dot and cross diagram to show the bonding ethane, so again recall, this is the structure of ethane. So every single bond here represents a pair of electrons. So if I were to draw a dot and cross diagram, it would look like this. Carbon, carbon, 1, 2, 3, 4, 1, 2, 3, 4, hydrogen, 1, hydrogen 1, hydrogen 1, hydrogen 1, hydrogen 1, and hydrogen 1. And I have my key. So this is the electron of hydrogen, and this one are the electrons of carbon. So show only the outermost electrons, this is what you will get. Dot and cross diagram, all single bonds. One pair of electrons make up one bond. Right? Okay. But is there another way of drawing a more complex alkane? So there's this medical condition which is called situs inversus totalis. So if you look at this diagram here, right, this guy's left lung is on the left, is on his usual left side. This is the normal. But in a person with this medical condition, the organs are actually flipped around. It's a mirror image. Notice if I were to fold the picture along the center line, they will actually overlap exactly on each other. So for organic molecules, something similar can happen as well, and we call this isomerism. Okay, so isomers exhibit isomerism. So isomers are compounds with the same molecular formula but different structural formula. So if we take a look at these two compounds here, one is okay, they are both C4H10. If I count 1, 2, 3, 4, 1, 2, 3, 4, both have 4 carbons. And if I count the number of hydrogens, both have 10 hydrogens. So they are both C4H10. But there are different ways of drawing this. Must I always draw it straight? No. Because carbon has 4 valence electrons. So who says that another carbon molecule cannot bond, another carbon atom cannot bond to another carbon atom in a different way? For example, this way. So 1, 2, 3, 4, straight chain. 1, 2, 3. Instead of the hydrogen here, the CH3, 1, 2, 3, 4, the CH3 is bonded to this carbon. Overall, each carbon still has 4 bonds. 1, 2, 3, 4. This carbon here has 1, 2, 3, 4. So all the carbon atoms in the molecule are all bonded to 4 other atoms. Right? So this actually completes the octet configuration. So these two compounds are possible to be formed, and we call these two different compounds isomers because they have different structural formula but they have the same molecular formula. Okay? So if I were to think a little bit more, propane for example, maybe not. Let's go to a little bit about this one first. Butane 2-methylpropane, both same formula, density roughly about the same, melting point, the melting point is about the same, boiling point is slightly different. See, slightly different. Actually, this is also slightly different. So why is it different? Density is equals to mass over volume. The mass is the same, but the volume is different. The volume of this, if you imagine this is a round little thing versus this bigger compound, right? So the volume, when the volume is different, the density would be different, but only very little. Boiling point wise is a bit different. Why is this different? Actually, this is not in the O-level syllabus, but for your information, if you recall butane, 2-methylpropane, they are both hydrocarbons. The predominant force between hydrocarbon molecules is van der Waals forces. Van der Waals forces depends on the MR. This is number 1 factor. And the number 2 factor is actually the surface area of the molecule. So the larger the surface area, the more extensive is the van der Waals force, because van der Waals forces exist between the surfaces. So if I have one surface that is like that and one surface that is like that, my van der Waals forces more extensive. The strength is the same, but it is more extensive versus two surfaces like that. There's less surface area for the van der Waals forces to form. So this is a less extensive van der Waals forces. So this is more extensive, less extensive. As a result, the boiling point is slightly lower. Right? Okay, now this is the interesting one. Propane. Does propane have any isomers? Earlier we did butane. Butane 4 carbons. Butane has 2 isomers. What about propane? Are there any isomers? Propane 3 carbon. C3H8. So this is one way to draw propane. Are there any other ways that I can draw propane? So this is the straight chain. So let's draw the next one and let's take a look. What if I were to draw it like this? Is 1 and 2 the same molecule? If you take a look and we count the number of carbons in the longest straight chain, 1, 2, 3. 1, 2, 3. So both have 3 carbons in the longest straight chain. So in fact, these two are the same molecules. So if I were to just replace this, let's say I remove this part here. I remove this one and remove this one and I swap it around. I will swap it around. So I swap my H over here now and I swap my CH3 back over here. So if you look at it now, don't these two molecules look the same? Yep. Yes, they're actually the same molecule. So propane has no isomers. The smallest, the simplest alkane molecule which can have isomers is actually butane. 4 carbon butane. Right? Okay, so now let's move on to the physical and chemical properties of alkanes. So this is actually the part which makes them very important to everything in your life and even the whole global economy. So physical properties, we are covering a few, from melting point to flammability. So let's take a look first. First of all, notice that the melting point increases as the number of carbon atoms increase. Right, so you recall predominant force between alkane molecules is van der Waals forces. So as the MR increases, the strength of the van der Waals forces will increase. So MR increase, strength of van der Waals forces increases. As a result, you need more energy to overcome the stronger van der Waals forces, and hence the melting point and boiling point will increase. So as a result, the state changes from gas to solid. Okay. Next point, density. If you notice one thing here, density actually increases almost exponentially from 0.00068 to 0.78. That is like a 1,000-fold increase. Why is that so? It's because if you remember the equation for density, density is mass over volume. The volume decreases drastically from gas to a solid. So the gas can occupy the whole room, but when it becomes a solid, maybe it occupies only a cube on the table, right? So the volume decreases exponentially as the state changes. As a result, the density increases exponentially as well, from gas to liquid. Liquids and solids roughly about there because not much changes already. So the main jump is from gas to liquid. Right, so take note, density increases. It increases, the trend is increases, but it increases a great deal from gas to liquid. Alright. Okay, solubility. This was covered before in chemical bonding. But essentially, you can remember this term. Like dissolves like. So basically, organic compounds will dissolve in organic solvents. For example, let's say, okay, iodine. Iodine is a non-metal. So non-metal, we can say this is a like as well. So non-metals dissolve very well in organic solvents. Like dissolve like. Water cannot really dissolve iodine. Water is not an organic solvent. Water is an inorganic solvent. So water actually doesn't really dissolve iodine very well. So it's like dissolve like. So if I have ethanol, organic solvent. Will it dissolve in hexane? Yes, it will dissolve pretty well, because like dissolves like, right? And you notice that when the iodine is dissolved to a very large extent, the color is different too. The purple color here versus this brown, yellowish brown color that you get when iodine is dissolved in water, right? The viscosity also changes as the MR increases. So basically, what is viscosity? It is actually the ability of the substance to flow. So if you notice from here, this is a very viscous liquid. This is a less viscous liquid. So why does viscosity increases as MR increases? So we imagine this molecule here. So let's say we have a long hydrocarbon chain. Okay, there are lots of hydrogens in, which I'm not drawing them in. So let me represent this as a long straight line versus one which is 2 carbons, shorter straight line. So imagine as you try to pour this substance out from the beaker, versus this substance out, there's a higher tendency for this long chain to entangle each other. So when I tilt the beaker to pour, so this long chain, this long lines inside, there's a tendency for them to entangle. So when they entangle, it becomes hard to move. Hard to move, it is harder to flow. Versus this short chain compound, smaller, shorter chain, less likely to entangle. So it flows more easily as a result. Okay, so this is viscosity. Flammability wise, it gets less flammable as your MR increases. The molecule gets larger and larger and larger. As a molecule gets larger, as your C gets to 100 or C something, the larger the hydrocarbon molecule, the more oxygen is required to actually combust the compound. Also, as it gets longer, the chain does not just remain straight. It is actually curved, bent, it entangles itself. So for something to react, the oxygen must reach inside the chain, and this is a bit hard when the chain is really long, and it sort of protects the carbon atoms on the inside from coming into contact with oxygen, so reaction doesn't really take place that fast. So as a result, it is less flammable. And in the event that it burns, because you need a lot more oxygen to burn this thing completely, so let's say we have methane, CH4 plus O2, CO2 plus H2O. So to burn 1 mole of methane, we need 2 moles of oxygen. If I increase this to C50, H 50 times 2 plus 2, 102, I will need a lot more oxygen. So as a result, it is harder for complete combustion to take place. So as a result, during incomplete combustion, we have soot that is formed. Soot is carbon, and this gives rise to the smokier flame. So take a look here. Butane torch, you are burning C4H10. Small molecule, easy to burn, and easy to burn completely. Candle wax, on the other hand, long chain alkanes, very large MR, so as a result, it burns incompletely. And during this incomplete combustion, it gives rise to carbon dioxide, carbon monoxide, and soot. That's why you see this yellowish color flame. This yellowish color flame is actually from the glowing of the carbon particles within the flame itself. So the carbon particles inside here, they are heated to a high temperature, and when they glow, when they burn, they give off this yellowish color which we perceive as the candle flame. Right? So the next part we'll move on to is chemical properties of alkanes. Two main ones which we need to learn: combustion and substitution. This is new. Right. Okay. So complete combustion, when you burn something completely, when you burn an alkane or burn a hydrocarbon completely, CO2, water, they are formed. Incomplete, sometimes carbon monoxide, sometimes carbon, but you always get water. Just balance accordingly. This is the new reaction. Substitution reaction. If we take a look at this equation here, straight away you will see why it is called substitution. Because when I have methane here, this is methane, CH4, one of the hydrogens is replaced with chlorine. So I have actually substituted out this hydrogen with a chlorine. Okay, simple reaction, right? So hydrogen here substituted with another atom. In this case, I sub it with a chlorine atom from Cl2. And for this reaction to take place, there must be UV light. So this UV light is used to start off the reaction. No UV light, no change. So when you write this equation out, you must include the UV light. This is the condition. This is the condition for the reaction to proceed. Okay, so can this reaction take place with any alkane or any hydrocarbon? Yes, it can take place. So if I replace this with C2H6 and I add chlorine gas, can I get C2H5Cl? See, I replace one hydrogen with chlorine plus HCl. Yes, it can take place. So substitution reaction occurs for all alkanes. Any alkanes, so long as you have the right conditions and you have the right reagent here. Okay? Alright, now let's move on to the next part, alkenes. Alkenes is a bit more complex than alkanes. Why? Because you see this equal sign here. This equal sign is not an equal sign actually. This represents a double covalent bond. So with this double covalent bond, you have double the reactions and you have double the difficulty. Not really actually. Okay, so you have more reactions which alkenes can undergo because of this double bond here. Physical properties wise, largely similar to alkanes. So let's take a quick look. Like alkanes, alkenes also form a homologous series. So if you take a look here, this is C2H4. The next one is just a CH2 difference. Okay, CH2 difference. They are called unsaturated. The unsaturated basically refers to the double bond. So long as a molecule has a double bond present, it is called unsaturated. If you have a lot of double bonds present, you are called polyunsaturated. Right, so alkanes have a general formula CnH2n. Alkanes, CnH2n plus 2. So this is alkanes. Alkenes is CnH2n. So like I said earlier, it varies by a CH2 and they have at least one carbon-carbon double bond. So what is the functional group of alkenes? It is actually the carbon-carbon double bond. So this is what we call the functional group of alkenes. The functional group gives rise to the properties of that class of compounds. Okay, it gives rise to the properties of this class of compounds called alkenes. So this is the functional group of alkenes, carbon-carbon double bond. And like alkanes, there are many ways that we can draw them. For example, let's start off with butene, C4H8, CnH2n, so n is 4, 2n will be 8. So this butene, I can put the double bond between the first and second carbon, or I can also shift it and put it between the second and third carbon, or I can also shift the entire CH3 upwards to the middle, and I get a different version of the molecule. So again, they are all C4H8, C4H8, C4H8. So if you recall, they have the same molecular formula, but different structural formula, which means that they are all called isomers, right? So how do we go about drawing this one? Let's take a quick look. So first of all, we know this is C4H8. So this is a 4-carbon chain, right? And this is an alkene, which means we must put in the double bond. So let's draw this out first. So this is the first one. Next one is to shift the double bond. So if we shift the double bond to the second carbon, this is what we get. If we shift it one more, this is what we get. But you realize this and this, they're actually the same carbon backbone. If I draw a dotted line here, and I do a 180-degree rotation, you realize that this actually flips around and it is same as this, right? So this and this are the same. So this is 1, this is 2. So after we shift the double bond, what we do next is to shift the carbon. So if I were to shift the carbon one step, let's say I shift this carbon one step to the front. Okay? So I shift the carbon one step to the front here. Notice this and this, they are the same. Okay? So I can't shift the carbon one step to the front. So let me shift it 2 steps from the front. So instead of shifting this carbon here, I now shift this carbon here, which means that I have something which looks like this. And you realize that this and this and this, these three are all unique structures. So this is a third form of the C4H8 alkene butene. So if I shift this carbon over to this carbon now, I will actually have this. And you realize if I count 1, 2, 3, 4, this and this is actually the same thing. This and this they are exactly the same thing. So for butene, it has 1 isomer, 2, and 3. These are 3 ways of drawing C4H8. So first of all, we shift the double bond, then we shift the carbon, right? Physical properties of alkenes, similar to alkanes. They are very similar to alkanes because essentially the difference between alkane and alkene is just the double bond. But the chemical properties are, this is the part where it varies by quite a bit. Combustion, all hydrocarbons undergo combustion. When they combust, they give you the same thing, carbon dioxide and water if it's complete. Incomplete, depending on the equation, it can be soot or it can be carbon monoxide. The next part is the addition reaction part. This is the unique part, which is only possible because of the carbon-carbon double bond in alkenes. So we will go a bit more in-depth into this area later on. Okay, so as I mentioned earlier, combustion, same across all hydrocarbons, but because alkenes have a higher percentage of carbon, as a result, when they burn, the flame is a bit sootier. So if I compare this ethene versus ethane, I will see the percent carbon for ethene is much higher than that for ethane. It is about 85.7 versus 80%. How do you count this? If you recall, it is actually 12 times 2 divided by 12 times 2 plus 1 times 4. This is the one for ethene. For ethane, it is 12 times 2 divided by 12 times 2 plus 1 times 6. So we get 85.7 versus 80%. So the higher the percentage of carbon in the molecule, the more sootier the flame will be. Right? Okay, so this is the new reaction which we are introducing today, addition reactions to alkenes. Take note. And this is possible because of the carbon-carbon double bond in alkenes, which we also call this the functional group in alkenes. So what can we add across the double bond? Notice I use the word across. Add across the double bond. Why is it across? Later on you will see. We can add hydrogen, halogens, for example, chlorine, bromine, etc., steam, which is water, and we can even add other alkenes. This one will be covered later on. So we do the first one first, addition of hydrogen or hydrogenation. We add hydrogen in a reaction, hydrogenation. So to add hydrogen, we need a catalyst. And we use nickel catalyst, and we have it at a 200 degrees Celsius high temperature. Why? If you recall from speed of reaction, the higher the temperature, the faster the rate of reaction. Okay? So what happens during this addition reaction? So why do I use the word across the double bond? Because when it adds, notice, the double bond actually opens up. And as a result, the two hydrogens get into the ethene molecule. So if I draw a dot and cross diagram, if I split just one bond, dot and cross, so if it splits open, it is actually like that. And when the hydrogen comes along, the bond forms between the H and the C. And this is across. This is across the double bond. Right? So this is the structural formula equation. This is the molecular formula equation. Depending on the question, you can write either this one or this one. Okay? So long as it has a double bond, it will add across the double bond. So if I were to ask you, what is the reaction for propene with hydrogen? It will simply be propene, draw the structure out. Try to always draw the complete structure because you are just starting to learn organic chemistry. It is sometimes a bit hard to write down the molecular formula straight away. It's easier to do this and then convert the formula into the molecular formula. So we add the hydrogen across the double bond, and what do we get? At the end of the day, we have a alkane. So this is the hydrogen that was added across the double bond. So when I add, I get an alkene. This alkene, it becomes an alkane. So any reaction when you see the conversion of alkene into an alkane, you will need to use hydrogen. Okay, addition reaction or hydrogenation. The next compound we can actually add across the double bond is bromine, Br2. So basically it behaves the same as hydrogen. If you imagine this, put it above, you get your H and H here. So now I replace H and H with bromine, and I get bromine and bromine. And the special thing about this is that bromine itself is reddish brown. So at the end of the reaction, when bromine is added across the double bond into the compound, it is gone, which means the color also disappears. So we can actually use this as a test for alkenes. So when I have an alkene in the test tube, I can actually add in bromine water. If I add in bromine water, and the bromine water color disappears, or what we call decolorizes, reddish brown liquid bromine or bromine water decolorizes, it means that this compound here will contain at least one double bond. So it can be a conclusive test of the presence of a double bond or an alkene. So this is a very common QA distinguishing test for alkenes. So take note of this. I have a video here from Nuclear Rabbit from YouTube. So let's take a quick look at what actually happens during the reaction. So this is alkane and this is alkene. Recall again, bromine water is reddish brown in color. So as it is added into an alkane, nothing happens. It remains yellowish brown or remains reddish brown because it doesn't add across the double bond. But when you add bromine water to alkene, notice the color disappears straight away. So the reddish brown color, the reddish brown bromine water is decolorized when it adds to alkene because it adds across the double bond alkene and it disappears. So as a result, you don't see the color staying in the solution here, right? Okay, so this test is used to distinguish between alkanes and alkenes. The next reaction is also an addition reaction, but this time around we add steam or we add water in the gaseous state. So what happens? Imagine this, HOH, we add this across. So from an alkene, when we add water across, it becomes an alcohol. From alkene to alcohol. We will cover more on alcohols later on. But for now, just take note, this is ethanol. If you see ETHA, basically it means the 2-carbon alcohol. Okay, conditions, phosphoric acid 300 degrees Celsius 60 atm. Take note, you must write this in. No conditions, no reactions. No reactions, no marks. Okay, so alkenes, ethene, add water, add steam, in the presence of this condition, you will get the alcohol. In this case, this is ethanol. Easy. So if I were to say add for propene, propene is C3H6. Structure wise, this way. Take note, the most common mistake is for students to draw in this extra hydrogen. So if you count, this carbon here has 1, 2, 3, 4, 5 bonds. This is wrong. Okay, so this is not supposed to be inside. Okay, so propene, add steam. What will I get? My steam basically adds across the double bond, so I will get an alcohol which looks like this. Is it correct if I draw it this way? Yes, both are correct. Okay, because you cannot control whether the water adds this way or the water adds this way. So both ways are fine. Both are still the same. Both are still alcohols. The last reaction is addition of alkenes to itself. We call this polymerization. We will cover more on this in the topic of macromolecules, but for now, if I were to draw the dot and cross diagram for an alkene here, this is ethene, dot and cross. So if I open this bond out, if I open one of the bonds out, it would look like this. This is the unpaired electron. This is the unpaired electron. So if I have one more carbon over here, which looks like this, if I have one more of the same molecule over here, this one actually can repeat itself. So if it keeps repeating and repeating and repeating and so forth, we get a very, very long carbon chain. And this is the process of polymerization to make a macromolecule. We will cover more about this in the later chapter. Right? Okay, so we have gone into the reactions of how alkenes can, what reactions alkenes can undergo, addition reaction, combustion reactions, but how in the world are alkenes actually produced? So you will need to know two ways. The first way is via cracking a long chain hydrocarbon. So this is a commercial process. Cracking is a commercial process. So during the cracking of a longer chain hydrocarbon, we get an alkene. We get an alkene, and sometimes an alkane. Or sometimes it could be a whole group of alkenes. It depends on the reaction. Right? Depends on the reaction. Ooh, I have 2 carbons too many here. This one should be like that. Okay? So by itself, the reaction will not happen. By itself, it will not happen. Because how do you actually break the carbon-carbon single bond when it is so strong? So you need the catalyst. And the catalyst we use in this case is aluminum oxide and silicon dioxide. Temperature of 600 degrees Celsius. So when you write the equation for cracking, catalytic cracking, you must put in the conditions of the reaction. Okay, straightforward. The other way in which you can produce alkenes is actually called dehydration of alcohols. This is not in the O-level syllabus. If you want to read more about this, you can find out more. It is called dehydration of alcohols. This is not in syllabus. You can read out more. So cracking produces our short chain alkenes, and actually at the same time it produces some hydrogen sometimes. And one of the most important uses of cracking is actually to produce petrol, because petrol, when you do a refining of crude oil, the amount of petrol which comes out is actually very little. But if you look around you, notice cars everywhere. All the cars need petrol to run. So where's the petrol from? It is actually from the catalytic cracking of longer chain hydrocarbons which we obtain from the fossil fuels after fractional distillation. Okay? Sometimes you may see this question in the O levels. So in this question, they have porous pot here. Take note, porous pot is actually the catalyst. It contains aluminum oxide and silicon dioxide. So these two are the catalysts for cracking to take place. So if you crack a longer chain hydrocarbon in petroleum, what do you get? You get a mixture of alkanes and alkenes. So this is just for your information in case it comes out in the O levels. So now let's move on to checkpoint 2. You can pause the video now, continue the video when you are done. Right, checkpoint 2. The structural formula of compound X is shown below. Deduce the structure of the original hydrocarbon and the compound which reacted with it and the name of the chemical reaction. So if you take a look here, you spot this straight away, HOH. So this is actually H2O. So if you think about this, it actually comes from the alkene. This alkene, and we do a steam addition and we get this alcohol. So if I were to remove this HOH, what would I get? It's actually just this. So this is working backwards. I'm showing you how to work backwards. If I pluck this out, remove in the form of steam, it means I have my double bond back here, because this came from here, right? So this was from here. So if I remove this one, my double bond must come back, and I'll have this compound here. So this is 1, 2, 3 carbons. So this is actually called propene. C3H6. The compound which reacted with it would be H2O, gas or steam, and the name of the chemical reaction will be steam addition. We can also call this hydration, because you're adding water, so hydration reaction. Compounds W and Y were bubbled into 2 separate test tubes containing bromine water. So when you see bromine water, straight away you must think, ding, alkenes. There will be one of them could be an alkene. Only compound W decolorized bromine water. So straight away we can deduce that compound W is an alkene because it decolorizes bromine water. General formula for W and Y are C2H8, where A represents the number of hydrogen atoms. Draw the structural formula of compounds W and Y and state the hydrocarbon family they belong to. So compound W is alkene, C2H8, so it's probably C2H4. Structure would be as such. Compound Y would be an alkane, and if it's C2H6, the structure would be as such. So this is ethene and this is ethane for alkane. In for alkene. Okay? Which one of the following is the formula of an alkene? CnH2n, general formula. So if we look around, we only have one, and that is compound number C. C4H8. Question number 4. Which one of the following is an isomer of butane? Butane, ANE, alkane. So it's CnH2n plus 2. So this is actually C4H10. So C4H10, if I draw the straight chain, 1, 2, 3, 4. Okay? 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. So all of these are all 4 carbons with 10 hydrogens. So which one of the following is an isomer of butane? So if we look at this one, this is a straight chain. Continuous carbon straight chain. Next one, continuous carbon 4. Continuous carbon 4. So basically these are just the 4 carbon straight chain butane molecule that is drawn in a different way. Next one, 1, 2, 3, or 1, 2, 3. This is a different form of these three similar same compounds here. So this is the isomer of butane. It is also C4H10, same molecular formula, different structural formula. Okay. Alright, so this is where we will stop for part 1 of the organic chemistry videos. Or should we do a little bit more? Alright, let's do a little bit more to cover the fats part. Polyunsaturated fats and oils. So unsaturated basically refers to presence of double bonds. poly means many double bonds. So if it's polyunsaturated, it means that in the molecule there are many double bonds. Okay, so this is an example of a saturated molecule. Why? No double bonds. This one, many double bonds. So this is an example of a polyunsaturated fat molecule. Right? Okay, the next part is on alcohols. We will continue with alcohols in the next video series.